when we graph sine of x, there's kind of a quote unquote easier way of doing it, or easy way of doing it, that I like to kind of think about. Let me zoom in just a tiny bit here. I feel like it's not, I feel like it's worse to see this today than usual. Does that look terrible? Is it hard to see? No, okay. It feels, maybe it's my perspective over here. So in graphing sine of x, we're going to plot angle values versus output values. But I really don't want you to plot all of them. So here's what we're actually going to do. We're going to use the unit circle. We're going to use a better pen. And specifically, we're going to think about the 4 quadrantal angles: 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians, and 0 or 2 pi. I guess technically 5 quadrantal angles. And the points associated with those are the point 1, 0, the point 0, 1, the point negative 1, 0, the point 0, negative 1. So when I start trying to graph sine of x, or I really should say 1 period of sine of x, because these are periodic functions, meaning they repeat themselves after so much x interval. I'm just going to plot these 5 points. So if I'm graphing y equals sine of x, well, the x part, the angle is 0, sine of 0 is 0. And if the angle is pi over 2, sine of pi over 2 is 1. Let's say this is 1 up here. And if x is pi, sine of pi is 0 again. If x is 3 pi over 2, sine of 3 pi over 2 is negative 1. And if x is 2 pi, well, we should be back where we started, because 0 and 2 pi are coterminal angles, and the sine and cosine value are always the same as they were before. So I'm finding sine of 2 pi should be the same as sine of 0, which is 0. And when I'm graphing sine or cosine, we'll see in a second, these are the 5 points I'm usually looking to plot, where I'm plugging in essentially the quadrantal angles. So the angles are 0, pi over 2, pi, 3 pi over 2, 2 pi. You could make a little list if you want, right? Like you could say, okay, x and y equals sine of x. If you want to be really kind of more precise about it, you say, okay, x is 0, y is 0, x is pi over 2, sine is 1, pi 0, 3 pi over 2, negative 1. I don't think you need to do this, but you could. Now, as far as the shape of this goes, it has a very kind of nice shape, for lack of a better word. It's going to look kind of like this. It kind of increases and then tops out right there. So 1 is the highest value sine can have. If you look at the circle, that kind of makes sense, right? The biggest y value on the circle is definitely 1. The smallest y value on the circle is definitely negative 1. So this is the top of the sine graph. So as you're drawing it this way, you want to kind of prepare for this to be the top so that you can be turning around and heading downward when you get to that point. Now, some people describe this as each section of the sine function looks like this first quarter just reflected somewhere. So this first quarter, I can reflect it over and get that second piece. The next piece, I can reflect that over the x-axis to the next piece. And then the last piece, I can flip that over to the last quarter. So when I think about drawing the sine or cosine function, I really think of it as 4 quarters, which isn't surprising because when we think about sine and cosine, we think about the 4 different quadrants of the unit circle. And sine goes through the same values in the first quadrant as it does in the second quadrant, the third quadrant, and the fourth quadrant. It's just that in quadrants 3 and 4, the values are negative. In quadrants 1 and 2, the values are positive. In fact, I want to emphasize that a little bit more. Right? Here's quadrant 1. Here's quadrant 2, quadrant 3, and quadrant 4. So there's the graph of y equals sine of x. A couple things to note. And I'm going to write this for everything because it's true. So the domain of y equals sine of x and y equals cosine of x is everything. Or you can plug in any angle and get a result. Some angles are nicer to plug in, like ones we know. Some angles are terrible, like 73 degrees. Or you can find sine of that too. It exists, but it's less nice. Domain is everything. The range for sine and cosine, the range is as low as -1 inclusive to as high as +1. I will tell you that the period of both of these functions is a length of 2 pi. So when I'm drawing these, I usually kind of draw little arrows at the end, right, to indicate that it keeps going. And what's going to happen is if you keep drawing this, the next 2 pi over is going to look like this exact thing just over there. And then again and again and again. It's the same thing over and over and over again forever, which is why we only usually draw one period or one period of it, because after you've done one period, you know the whole shape. And then lastly, the amplitude of this sine function is 1. So when I think about what the amplitude means, the amplitude is kind of how far above and how far below the middle it goes. Some people would say just take the entire length of the range. What is the length of the range of this function? How long is the range? A little longer than 1. Exactly, it's 2. So I think I misled you. I said take the length of the range because I was about to finish my statement. Take the length of the range, which is 2, and divide it by 2. That'll give you the amplitude. So here the amplitude is 2 divided by 2, which is 1. The shortcut way of doing, which we'll see on the next page, is you just take the coefficient of the sine or cosine function and make sure it's positive. So if it's negative, you just turn it to a positive number. All right, let's do the same thing for cosine. So graphing cosine, again, I'm going to start at the angle 0, and cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is 1. Whenever you plug in 0 and 2 pi, you should get the same output value, the same y value. Now, something about graphing cosine to be aware of is it's going to go like this. But when I get to this endpoint here, right, I shouldn't be shooting up above it. Right? 1 is the highest value. So at 1, either 0, 1, or 2 pi comma 1, that should be the top, meaning it should kind of look like this. Right? It's not going above that point after it's turning around at that point. When you graph sine or cosine, it should be relatively curvy. In fact, I would encourage all of you to actually look at the graph on graph utility just to kind of really see what it looks like. Because although it's not like absolutely vital that you graph it perfectly, it is good to graph it relatively close to how it actually looks. So, whoops, where'd you go? Come on. Sorry, the mouse is in the way here. Just so you all can see what an actual very nice graph of sine looks like. Oops, not sim, sine. There you go. There's sine of x. It looks lovely. And it just keeps going on and on and on forever, never, never. And you can plot, or you can grab some of the nice points there. Right? There's all the points weaker. Now there's other points, which might be harder to find. Yeah, they probably don't show up on here easily. Right, but you could plug in other angles and get, for example, just as one other noteworthy point for sine, if you let x equal pi over 6, y is going to be sine of pi over 6, which is 1/2. Oh, sorry. Yeah. Yeah, maybe you don't cover up a trend here. Sorry. If x is pi over 6, then the y coordinate's 1/2, which is exactly this point right here. And if x were pi over 3, sine of pi over 3 is root 3 over 2. Now, so I don't want to plot all of those points because it's like 12 points to plot those in a graph the whole thing. But if you wanted to kind of get a slightly better idea of how it looked by plotting more points, you could. Or you could look at this. But when I graph sine or cosine, when you graph sine or cosine, I really, really encourage you to do it by graphing, plotting these 5 points, and then trying to make it look as nice as possible. There was one other thing I wanted to mention here. Where'd you go? Yeah, those 5 points. Sure. Oh, the other way I think about sine and cosine is, I remember sine has this pattern. Starts in the middle, top, middle, bottom, middle. So, and then cosine is top, middle, bottom, middle, top. Essentially, when you're graphing sine or cosine, you're always hitting the middle and then going away from it. So middle, top, middle, then bottom, then middle, then top, then middle, then bottom. And both of them do this. So you have to go from the top. You can't go straight from the top to the bottom, or straight from the bottom to the top, right? You have to stop in the middle first. So just be careful when graphing these, because I've definitely seen people in the past go like, here's this point, and then the next point that you're like way down here, which isn't the next point. So you always have to kind of go in between. When you're going from the middle, or the top to the bottom, and the bottom to the top, you have to stop in the middle. But really what I would do is just plot these 5 points this way. So, okay, yeah, I know I need these 5 angles, 0, pi over 2, pi 3, pi over 2, and 2 pi, and then find the corresponding y values. Okay, so those are the basic sine and cosine graphs. Now we're going to transform them a little bit. Not a whole lot, just a little. So we can use our usual techniques for stretching and shifting these graphs. And there's all the things. We're going to have y equals a times sine of b times x minus c plus d. We've already talked a little bit about what some of these things are. So A, so in a previous era, we might have said A was the vertical stretch, right? When you multiply the function on the outside, you stretch it vertically. But the word we're going to use for that here is amplitude. So I would actually say the absolute value of A is the amplitude, because that coefficient could be negative. If I had a negative out front, what would that do to the function? Yeah, it would flip it over the x-axis. So if you had like -2 sine of x, the amplitude would still be +2, because amplitude is always positive, but it would be the sine function flipped over. B is going to be how much we modify the period by. So it is going to be a horizontal stretch or compression, but we really just think about it as the period modifier. So whatever is multiplying x in your trig function, sine or cosine, is going to change what the period is. And we'll talk about that a little bit more when we get to an example like that. And then we have our usual easier things to think about. This value c here is just how much it shifts left or right. And adding d on the outside is going to be how much it shifts up or down. All the usual kind of shiftiness, right? Not that the functions are shifty, but you know what I mean. All the usual shifting. So if d is positive, you shift it up. If d is negative, you shift it down. If c is positive, you shift it. Well, so if you have x minus a number, you shift it to the right. If you have x plus a number, you shift it to the left. Okay. A couple notes which you already kind of mentioned, but I just want to say them explicitly here. For the parent functions, y equal to sine of x and y equal to cosine of x, the amplitude is 1. And again, for the parent functions, y equal to sine of x and y equal to cosine of x, the period is 2 pi. And the reason the period is 2 pi is because after you've gone one full revolution around the circle, you're going to just start getting the same trig values again and again and again, right? They're just going to repeat. Sine's going to go 0, 1/2, root 2 over 2, root 3 over 2, 1, so on, so on, so on, so on, so on, so on. And when you get to 2 pi, the sine values are going to repeat again, right? You're going to get 0, 1/2, root 2 over 2, root 3 over 2, 1, and so on and so on and so on. So you're just going to keep doing the same thing over and over and over again. So sine and cosine both just do the same thing after you've gone through one whole period of 2 pi. Whereas I should really, really extra emphasize here, after the angle has gone from 0 to 2 pi. Okay, so let's graph something different. Let's graph y equal to 3 sine of x. And so you'll notice I've left the y-axis unmarked so that we can kind of make it whatever we want it to be. Previously, I said 2 marks up was 2, but that's not going to work for me, or was 1. I'm going to say now this is 1, this is 2, this is 3. -1, -2, -2. For this function, the only thing I'm going to make note of really is that the amplitude is 3. I guess I would also probably remind myself that the period is 2 pi. So what that's going to do for us is going to stretch it 3 by a factor of 3 away from the x-axis. So instead of getting the original sine function, which looks like this, which goes up from 0 and then to 1 and then to 0 and then to -1 and then to 0, which I'm just going to graph like that. So there's your original sine function in green. But now I'm multiplying it by 3. So 3 times 0 is still 0. 3 times 1 is 3. 3 times 0 is 0. 3 times -1 is -3. 3 times 0 is 0. So those are the 5 important points for this graph of y equals 3 times sine of x. It's just getting stretched vertically. There's our graph of y equals 3 sine of x. The same as y equal to sine of x. Right, there's our previous, oops, you can't really see it, sorry, 1 second. The same as y equal to sine of x, just stretched further away. Now I know the scales aren't the same on these graphs, but the idea is that this one is getting stretched further away from the x-axis. Oh, yeah, so that's an excellent point. I did kind of blow it there, right? Yeah, sorry, I went too low because I wasn't looking over to the left here. So it should have really looked, that's terrible. I feel like I need to graph again. Sorry about that. No, you're totally right. I should definitely go as high as these. So it's easy to make a mistake when you're graphing these, right? It's easy to get off by a little bit if you're not looking over. So let's graph it again just to make it better. Sorry about that. So yeah, this should have been starting here and then pi over 2 comma 3, pi comma 0, 3 pi over 2 comma -3, and 2 pi comma 0. This one doesn't look as good, but it's still a sine graph. So there's our y equal to 3 sine of x. If you want, so if you feel like your graph maybe doesn't look so hot, which I'm certainly guilty of plenty of times, and my graphs do not always look great, you can label your points. Right? You can be like, well, I'm going to say that's pi over 2 comma 3. That's pretty obviously pi comma 0, but you could label it. And that's 3 pi over 2 comma -3. Just so that everyone's really like, okay, I know their graph might not look excellent, but they obviously know what's going on because they know what the important points of the graph are. So when I'm graphing sine or cosine, I'm really kind of focused on making sure I hit those 1, 2, 3, 4, 5 important points. Yeah, you could plot more of them, but I don't think you need to. It's more about knowing the shape. Together, sine and cosine are called the sinusoidal functions. So, and you'll probably see that word next quarter when you take either 16A or 17A. Yeah, together they're referred to as the sinusoidal function. So when someone says that, they just mean sine or cosine. They're just trying to be fancy. Let's look at a couple more examples. So now we have y equal to cosine of 4x plus 1. Here we have a couple things going on. We have a shift up by 1. And when I have an upward shift, what I usually like to do is I like to draw a new middle. So usually if you haven't shifted it up or down, the middle is the x-axis, right? Definitely looking back at this previous example, right? The middle of this graph vertically, right? You're 3 above, you're 3 below, the middle is y equals 0. But now we're shifting everything up by 1. And so to me, it's really easiest to say, well, I'm going to have a new middle. My new middle is y equals 1. It's not a horizontal asymptote. It's just the new middle. You don't have to do that. Clearly here, we don't really need to do that because it's already on grid line. So you just be like, oh, there's y equals 1. I'm not going to draw this thing. If you're drawing this not on graph paper and you're just making up your own coordinate system, I often think this is helpful. All right, the other thing that's true here is the period is different. So I want to explain to you how the period works. I said before, to get one full period, we have to go from 0 to 2 pi. Or specifically, our angle has to go from 0 to 2 pi. So in the previous examples, our angle was x, right? We're taking sine of x, cosine of x, etc. In this particular example, y equal to cosine of 4x, what's playing the role of the angle? 4x, right? Whatever you're taking sine or cosine of, that thing is your quote unquote angle. So our angle is 4x. And we need 4x to go from 0 to 2 pi to get one full period. So we need 0 to be less than or equal to 4x to be less than or equal to 2 pi. That's going to give us one full period. But I'm not graphing 4x on the x-axis, I'm graphing x, or I'm plotting x, right? I'm not, this doesn't say the 4x axis, it says the x-axis. So I need to actually know what my x values are going to be. So I'm going to divide everything by 4. 0 divided by 4 is 0. 4 divided by 4 is 1x. And 2 pi divided by 4 reduces to pi over 2. So the period of my new graph is going to be much less. The period is going to be pi over 2 instead of 2 pi. So I'm going to go from here to here. That's kind of my ending. So if it's inside, if it's affecting x, then it's shorter than. Right. So so I should say, if the number multiplying x is larger than 1, it's going to squash it horizontally. And if the number multiplying x is less than 1, like in the next example, it's going to stretch it horizontally. We'll see that in the next example. So what I'm going to do now is I'm going to think about, well, I know cosine starts high, then goes middle, then goes low, then goes middle, then goes high. So we could say, well, I'm going to have, let's see, my period is, sorry, my amplitude is 1. So I'm going to be 1 above 2 and 1 below at 0. Cosine starts above, and then I have to cut this into 4 equal quarters. So there's the middle that way, and I'm cutting that. So I'm going to have top, middle, bottom, middle, top. Sorry, I actually plotted that there. It's kind of a scrunched graph here. And then you could draw more of them if you wanted to. Another way to think about this is instead of saying that you have one period in pi over 2 length, you have 4 entire periods in the length from 0 to 2 pi. So if I went from 0 to 2 pi, I would have 4 whole periods of this function. Yeah, we got time. Another way to think about it is normally when we're finding our 5 important x values, and we're thinking about what values we're putting in, we're picking the usual nice quadrantal angles. 0, pi over 2, pi, 3 pi over 2, and 2 pi. And cosine of those values, cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is -1, cosine of 3 pi over 2 is 0, cosine of 2 pi is 1. But again, right, we're not actually plotting 4x, we're plotting x. So to get from 4x to x, we divide by 4. 0 divided by 4 is 0. Pi over 2 divided by 4 is pi over 8. Pi divided by 4 is pi over 4. 3 pi over 2 divided by 4 is 3 pi over 8. 2 pi divided by 4 is pi over 2. So these 4 or 5 points here between 0 and pi over 2 are 0, pi over 8, pi over 4, 3 pi over 8, and pi over 2. Just so if you're trying to get a better idea of where those actually are falling on the x-axis. Because again, these are the points I think you should be emphasizing that you're plotting when you're graphing sine or cosine. Questions so far? Let's look at another. Okay.
That sounds kind of like silly. But
Nope.
Is it weird to ask like why? Like why see them on a graph? Like
why graph this at all?
yeah.
Well, I mean, so I would definitely not say that's silly. We graph things a lot of the time to have an idea of what it looks like, because what this graph is representing for us is every possible input and output combination. Right, so like we know sine of pi over 6 is 1/2, or sine of 2 pi over 3 is positive 3 over 2. But there are literally an infinite number of inputs you could put into the sine function and get out values. And this graph, the one we started with, this first one here, this is telling us, well, I don't know exactly what everything is, but I could look at it and be like, okay, well, if I plug in something a little less than pi over 2, it's a little bigger than 0. And it just gives us kind of a nice visual representation of what things look like. So that is often the reason for graphing a lot of things, right? Because there are lots of other equations that we solve, and sometimes the solution is a lot of different things. And the graph is kind of the best way of being like, okay, well, this is what our set of solutions look like. It's every point on this curve or on this line. Trigonometric functions like sine and cosine are also used to model certain behaviors. One example I imagine you'll probably all see next quarter is they talk about make up a sine or a cosine function to model the amount of sunlight in a day over the course of a year. So it's summer, right? You've got the most amount of sunlight or the most hours of sunlight in the day. And at the depth of winter, you've got the least. And it definitely follows the sine kind of idea where you've got the most here being, 14 hours of sunlight a day and the least being like 10. I don't know what the numbers are actually, but it's definitely an actual function that models real things in life. So that's one reason we're graphing it. Let's look at this next one. So here, I'm going to try and show you exactly how I would do this, and I would want you to, if I asked you to graph this on a test, here is how I would want you to graph it. First, make note that the amplitude is 3. The vertical shift is down 1. And the period is going to be, so the short way of doing it is the period is going to be 2 pi divided by the coefficient of x. 2 pi divided by 1/2 is 2 pi times 2 over 1, which is 4 pi. In fact, I feel like I should go back to a previous page, the second page of notes, and point out that the period, specifically the period, is equal to 2 pi divided by the coefficient of b. That's the fastest way of finding it. And really, it's exactly because of what we did previously, right? When we were finding the period of the previous one, we took, well, in fact, does everyone have that? So I can move back. Okay. So, right, if I was going to find the period here, I could say, well, I know I need 1/2 x to be between 0 and 2 pi. This is not work you need to do when you're doing it. I'm just showing you. How am I going to isolate x? What am I going to divide each side by? Or what am I going to, I guess you could say, what am I going to multiply everything by? It's probably an easier way of doing it. What am I going to multiply everything by? To get x by itself, if I have 1/2 x and I want to get rid of the 1/2, I'm going to multiply by 2. Or divide by 1/2. I'm going to say divide by 1/2 just because if you divide by 1/2, oh, look, that's exactly what we're doing to get the period. You're taking 2 pi and dividing it by the coefficient of x, which is 1/2. And then when you do that, 0, everything is 0. 1/2 x divided by 1/2 is just x. And 2 pi divided by 1/2 is 2 pi times 2, which is 4 pi. So that's the reason why when you're finding the period, you take your 2 pi and you divide it by whatever the coefficient of x is. Because that's literally how you find the new period. So I need to change my, so I was a little over. I'm going to change these. I'm going to make this pi instead of pi over 2. This is 2 pi. This is 3 pi. This is 4 pi. Because what I do when I'm finding my 5 important points is I take my entire period, which has a length of 4 pi, and I'm going to divide it into 4 equal quarters or 4 quadrants, because the important points come at the end of each quadrant. So if I take 1/4 of my period, which is very easy to calculate here, it's 1/4 times 4 pi, which is just pi. I get the beginning of a new quadrant after pi. So my first quadrant starts at 0, and then my next quadrant starts at pi, and then at 2 pi, and then at 3 pi, and then at 4 pi. So these are my 5 important points: 0 pi, 2 pi, 3 pi, and 4 pi. And then I just think about, okay, well, how does cosine look? Is cosine the one that starts in the middle and then goes up and then back and then back and then back? Or is cosine the one that starts high and then goes down and then down and then up and then up? Cosine starts high. So cosine starts high, sine starts in the middle. None of them start low unless you flip them over. So negative cosine would start low and then go middle and then go high. And negative sine would still start middle, but would go low first instead of going high first. So I'm not going to start at 3 though, because I'm shifting down 1. So here's my new middle line. And my amplitude is 3, meaning I'm going to go as much as 1, 2, 3 above -1 and 1, 2, 3 below -1. And typically on my y-axis, I only like to label the y values which are the high, the middle, and the low, because I don't really care about anything else. Cosine starts high at 2. And we can check if you want, right? If I plug in 0 for x, cosine of 0 is 1. 3 times 1 is 3. 3 minus 1 is 2. Oh, yeah, I get 2. And then cosine goes to the middle. Now, here's where you have to be extra careful. I'm not looking for that point right there. I'm looking for that point right there. My next important x value is pi, and cosine goes from the top to the middle. And then from the middle to the bottom. And then back from the middle, sorry, from the bottom to the middle, from the middle to the top. Notice I am not at all thinking about the x-intercepts. Yeah, there's going to be some x-intercepts here. It's going to cross the x-axis, but I don't really care about those points. I really care about these 1, 2, 3, 4, 5 points. The cosine is going to look something like this. There's my y equals 3 cosine of 1/2 x minus 1 graph. And if you really want to, you could check these points, right? If you plug in pi, Cosine of pi over 2 is 0. 3 times 0 minus 1 is -1. You plug in 2 pi. Cosine of 1/2 times 2 pi is pi. Cosine of pi is -1. 3 times -1 is -3 minus 1 is -4. So getting that value. You don't need to check them, but you do need to think about how we're like, you know, I should say, you just need to, words work. When I'm graphing this, right, I'm really thinking about the shape, right? We could check all these values, but I'm like, okay, I can find my 5 important points. I know that the cosine shape looks like this. And so then I'm just going to kind of put it all on the graph and not think too hard about finding the values. What I would say you should do if you are concerned about whether your graph looks right or not is after you have graphed it, maybe look at Desmos and see, does my graph look right? I would really encourage you to do that after you graph it, though, because it's good to practice graphing it without extra assistance. And that's like a weird like thing on the, I'm like, what's on the bottom of this desk? It's like this word is the name of the desk. So I'm not just totally weird. Okay. Let's look at, I've got more examples than this. Yeah. We've got time. So, oh, question, Malik. Sorry, can you say that one more time? You didn't understand what? Sure. So for the normal cosine graph, the 5 important x values are 0. Well, in fact, for sine or cosine, right? The 5 important x values are the quadrantal angles. In degrees, 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees. In radians, 0 radians, pi over 2, pi, 3 pi over 2, 2 pi. The way I found the new important points is I said, well, I know that in the original sine or cosine graph, all of my important points are exactly the quadrantal angles. They're 0 and then 1 quadrant away, 1 quadrant away, 1 quadrant away, 1 quadrant away. The difference in this example here is that the length of the quadrant has changed. Right here, the entire period was how much? 4 pi. So if you take 4 pi and divide it into 4 equal quadrants, how much is the length of each quadrant? Pi, exactly. Now, for one starting at 0, which so far all of our examples have been, it's fairly straightforward. Start at 0, and then the next quadrant is going to start at pi. And then add pi, you get 2 pi. And add pi, you get 3 pi. And add pi, you get 4 pi. And it should be true that from your beginning to your end should be the length of the whole period. From 0 to 4 pi definitely is. So that's how I'm kind of thinking about it, is I'm taking my new period length, dividing it by 4 to get the length of each quadrant, and then just saying, okay, 0 plus 1/4 of a quadrant, plus 1 quadrant, plus 1 quadrant, plus 1 quadrant, plus 1 quadrant gives me my 5 important points. Let's look at another example. Let's look at y equal to -4 cosine of 2x. So what's my amplitude here? It's negative. It's just positive. So the amplitude is always going to be positive because that's what it's kind of like talking about distance, right? Distance is always positive. Amplitude is the same kind of idea. It's kind of just how far you're moving from the middle. And we would always take that as a positive number. But we are going to have a vertical flip. The negative sign is going to be a vertical flip. Meaning, instead of starting at the top and then going middle and then bottom, we're going to start at the bottom and then go middle and then go top. And then, what's our new period going to be? Well, it's going to be, 2 pi divided by 2, because 2 is the coefficient of x, which is just pi. And now to find my 5 important x values, I'm going to take my period and I'm going to do 1/4 of my period. That's going to be 1/4 times pi, which is just pi over 4. My first point is going to be 0. My second point is going to be what? How long is the quarter of my period? Pi over 4, right? Because I'm right. All my 5 points are a quarter of a period away. My first point is 0. My next point's a quarter of a period away, which is pi over 4. My third point is a quarter of a period away. And pi over 4 plus pi over 4. You can write that. I would honestly probably not simplify it. I would leave it as 2 pi over 4. I might also simplify it, but when I find the next point, it's going to be easier to add another quarter of my period to 2 pi over 4. And then my last point is going to be 3 pi over 4 plus another pi over 4, which is 4 pi over 4, which is pi. And from 0 to pi is 1 full period, so we're good. So I know I'm going to have, let's see, so cosine is going to start at the bottom and then down at -4. So we're going to start down here. And then my next important point is in the middle, and it's when x is pi over 4, which is halfway between 0 and pi over 2. And the next point is going to be at pi over 2 at the top. And the next point is going to be at 3 pi over 4, which is halfway between pi over 2 and pi. In the middle again. And then the last point is going to be at pi, it's going to be -4. It's going to look pretty steep. There's one period of -4 cosine of 2x. Yeah, we got time for one more, for sure. Questions about this one? Next one's gonna be a little more, we're gonna add a challenge. You guys ready? Yeah.
With 1/4, but we need 4 parts within the period of.
The period of what?
Pi.
Yeah, I didn't hear it, sorry. Exactly what he said. Yes, it's 1/4 pi because we need 4 parts in the period of, in the length of our period, which is pi. Perfect. Okay, so let's amp up the challenge here. Let's say we want to graph y equal to 2 sine of 2/3 x. What am I going to pick here? Sure. Minus pi. Let's just do that. Sorry, let's make it plus pi. 2/3 x plus pi. So we've got a new addition here. Well, let's talk about the things we know. We know the amplitude is 2. How am I going to find the period? Well, it's going to be 2 pi divided by what? 2/3. Or more easily, it's going to be 2 pi times what? 3/2. And nicely, the 2's cancel. And you get 3 pi. Now, before I guess, well, I can do one more thing. I can say that 1/4 of my period is going to be 1/4 times 3 pi, which is 3 pi over 4. But there's an additional twist here. This function also has a horizontal shift. All right, we're adding on the inside of the function, so it's going to shift it to the left, which means our starting first point isn't 0. Right? If you plug in 0 there, if you plug in 0 for x, you don't get sine of 0. You get sine of pi, which is not where we start at. So we want our initial angle to be 0. So here's how you find your shift. So here's how we find the horizontal, also known as the phase shift. And there's actually a really easy way of doing it. Take the inside of the trig function, or also known as the angle. So take your 2/3 x plus pi and set it equal to 0. Because we really want to start where the angle is 0. That's exactly what we're saying. 2/3 x plus pi should start at 0. Now we're going to solve for x. So subtract pi from both sides. So 2/3 x equals negative pi. And what should I multiply both sides by? 3/2. 3/2 times 2/3 x equals 3/2 times negative pi. To end up with x equal to negative 3 pi over 2. That's your first point. Instead of 0, our first point is negative 3 pi over 2. How am I going to find the second point? Well, it should be how far away? 1/4, 1 quadrant, which is how much? 3 pi over 4. That's my 1/4, or it's 1/4 of a period, or 1 quadrant of a period. Same words essentially. So my second point is going to be my first point plus 1/4 of my period. All right, well, I need common denominator. Negative 3 pi over 2 becomes negative 6 pi over 4 plus 3 pi over 4 is negative 3 pi over 4. There's my first point. There's my second point. My third point is going to be super easy. I'm just taking my previous point, negative 3 pi over 4, and adding 1/4 of my period, which is 3 pi over 4. What's negative 3 pi over 4 plus 3 pi over 4? Everybody? Thank you. Yes. Okay. So I make sure everyone's with me. All right. Good. All right. Then my fourth point should also be easy. It's going to be 0 plus another 3 pi over 4, which is 3 pi over 4. And then finally, my fifth and last point is going to be 3 pi over 4 plus another 3 pi over 4, because I'm adding 1 more quarter. And we're going to get 6 pi over 4, which reduces to 3 pi over 2. So this one happens to be kind of extra nice in that it's kind of symmetric about the y-axis, right? You have a point, the origin, a point, a point. So here's how this one's going to look. So I'm just going to make marks that seem like they might be about the right length. I don't really know. There's my negative 3 pi over 2, my negative 3 pi over 4, my 0, my 3 pi over 4, my 3 pi over 2. And then it's going to be 2 sine. So the sines start at the top, the middle, or the bottom? Starts in the middle. So we're starting in the middle at our leftmost first point. And then we're going to go to the top. And that's going to be 2. Now, here's where you can be kind of freewheeling. Your scale can be however you want it. You can actually just draw the thing first and then mark it so it's right. I'm going to try and be somewhat accurate. Maybe not. So here's what I'm going to say. 3 pi over 4. 3 times pi is close to 9. So essentially I'm going to be like, pi is about 3. Not really, but okay, close enough. 3 times 9, 3 times 3 is about 9. 9 over 4 is a little bigger than 2. So this length on my graph is about how long 2 is. So if I was going to try and make the scale the same, I would try and maybe make it like, okay, that's too high. That's 1. But if you went way higher than that, that would be okay. Your scale on the X and Y axis does not have to be the same. It's good to not make it too wildly different, but so at my next point, I'm going to be high, and then back to the middle, and then low, and then back to the middle. So here's what my graph should look like. Now, you might notice not all my quarters are equal length because I'm not a great drawer. That's okay. Right? My last quadrant there is probably a little longer than it really should have been. No worries. Last thing I want to say, just so you don't get confused, I think there's one question on the homework where it has you graph like y equal to, I don't remember what it is exactly. It's something like 2 minus cosine of x or something like that. People always get thrown off by this one. Just rewrite it as negative cosine of x plus 2. That's going to give you a vertical flip for cosine and then a shift up of 2, or whatever the actual question is. But that's the idea, right? If you've got something minus a trig function, just write the trig function first so it looks more like the standard way of writing.